Okay, we're into, I'm going to call it the last chapter, chapter 4. I know we do one section of chapter 5, but that's it. So it's going to get lumped in the same time we do chapter 4. But this is extending calculus to the next big topic. So up until this point in the class, you can classify everything we've done as what's called differential calculus, because we've been primarily and almost exclusively finding derivatives. Right? The limits chapter, or the limit sections of the first chapter, was set up to take derivatives, and then we took derivatives for a good long while. We took derivatives of exponentials and logarithms, and then the whole entirety of chapter 3 was just looking at applications of derivatives. Chapter 4, and if you continue on with there's a secondary course to this at most other schools, so if you transfer or you take it somewhere else, I know, for instance, City College teaches the second course in this sequence. It continues into what we call integral calculus, and integral calculus is all based on this process, antidifferentiation. So we have 3 things to do in this section. The first is we need to talk about how we find an antiderivative. And then we need to talk about the actual process of integration. And there's 2 types of integration. There's indefinite and definite, and we're going to be focusing on indefinite first. And that'll make more sense when we introduce what definite is. And then we're going to be looking at what's called initial value problems. And we'll talk about what those are and what that means. So let's talk about our new terminology. Excuse me. So antiderivatives. An antiderivative, as it says, you might have guessed, is the reverse of a derivative. It's the opposite. We can think of this as a function whose derivative is given to us. So up to this point, I've been handing you functions, or the homework or quizzes have been giving you functions, and you've been asked to find the derivative. Now, when we're doing antiderivatives, you're going to be given the derivative, and you're going to be asked to find the function that it came from. So I have some examples here. We have 3 functions, f prime of x, g prime of x, and s prime of t. And our goal is to determine the functions f, g, and s that these derivatives came from. And we're going to make a couple educated guesses right now. And if you do that, you might come up with a couple different things. The big question is, we'll focus on f of x first. What function, what f of x, has derivative of 2? So if you think about your functions and you're taking a derivative, what would you need for the derivative to be 2? Well, the one that most people can come up with is 2x. If f of x equals 2x, then f prime of x equals 2. And that works out no problemo. So now when we think about g of x, g of x is 3, or g prime of x is 3x squared. So we know when we take derivatives to get to the second power, we should have started with the third power. And so usually we stick with x cubed. Now, as it turns out, if we take the derivative here, g prime of x becomes 3x squared. And so we have our answer immediately. Now for s prime of t, if s prime of t is 4t, to get to a linear power, a first power, we know that we should have started with, by our power rule of differentiation, a second power, t squared. So now let's look at how we would do this more generally. Because we know our constant rule of differentiation, the constants stick around, a lot of times what you'll see people do is say, okay, I'm just going to make this 4t squared, because I know that the 4 can stick around if I take the derivative, and to get t, I need a t squared. And then you take your derivative, s prime of t, and you get 8t. You say, okay, this is 8t, but I want it to be 4t, so I need to divide by 2. And since constants stick around, I need to divide by 2 here. And so we end up with our final answer is S of t equals 2t squared. So the process we're kind of outlining here with f of x, you can the simpler they are, you can guess easier. Constants are easy. For g of x, we guessed and we turned out to be right, so sometimes you can get lucky. And for s of t, we took a little more analytical approach and we said, okay, we know our constant rule of differentiation. We know how linear functions are the result from differentiation. We need a quadratic. Then we set up that basic function. We say, okay, this is off by 2, so I need to divide this by 2 to get what I started with, which means I divide my original function by 2, again, because constants stick around. So we end up with 3 antiderivatives but as it turns out, there's a lot more answers we could have had. So this operation of determining the original function, finding that antiderivative, this process is called antidifferentiation. Now it's math, so we like to shorthand things. So let's define antiderivative before we get to the shorthand version. So a function, capital F, is an antiderivative of little f if for every x in the domain of little f, f prime, capital F prime, of x is equal to little f of x. And the antiderivative, so notice that this is an antiderivative here, but the antiderivative of f of x is f prime of x plus some constant. So this is where c is a constant. And the reason for that is the reason why these aren't the only 3 answers in this example. So we're going to take a look at these 3 functions, f of x, g of x, and h of x. And we're just going to think about what could these be antiderivatives of. So we take derivatives, f prime of x, derivative of x cubed is 3x squared. G prime of x, derivative of x cubed is 3x squared. Derivative of minus 5 is 0. And h prime of x, derivative of x cubed is 3x squared. Derivative of 0.3 is 0. So you can see that all 3 of these have the same derivative, which means that f, g, and h are all antiderivatives of 3x squared. Because when we take the derivative of each of them, we can get to 3x squared. And so the big takeaway here is that antiderivatives are not unique. There are, in fact, infinite antiderivatives for any function, any differentiable function. So when we talk about the antiderivative, what we really want is to include all of these. So the antiderivative would be x cubed plus c. This is the antiderivative. Antiderivative of 3x squared. Because if we have this generic plus c, then all of our functions are accounted for. The plus 0 in f is accounted for. The minus 5 is accounted for. The plus 0.3 is accounted for, along with every other combination of constants that we could come up with. And so this allows us to not worry about how many antiderivatives we need to find, or is it this one or that one. It's just, hey, we're going to find the general antiderivative, and it's the antiderivative. And as we move forward, we'll look at how we find specific antiderivatives of functions that we want. So I have 4 problems here for you to practice. And you should try this out. Use the same process that I just did in the last couple examples. So come up with a guess. I'll do part A with you right now to kind of get you on the right track. So x squared, to get to x squared, we need an x cubed. Now if I take my derivative of x cubed, I have 3x squared. And I don't want 3x squared, I just want x squared. So I divide by 3 and I divide by 3. And since we want the antiderivative, that was the terminology we used, we're going to say x cubed over 3 plus c. So try this out on the next 3. Pause the video and actually do this. I'm going to start going through it now, so if you haven't paused, do it now. So our antiderivative for 3x to the 4th, it should be 3x to the 5th. But if I take the derivative, I'm going to get 15x to the 4th. That's too many. I have to divide by 5 to get back to 3. So I divide by 5, which means the antiderivative will be 3/5 x to the 5th plus c to account for all the constants. Now for e to the 3x, we know that the derivative of e to the 3x, if we look at that just in isolation, would be 3e to the 3x, which means that my antiderivative here would just be e to the 3x plus c. And then in this last one, I'll be doing a couple different things. So the antiderivative of x cubed would have to be x to the 4th, and if you take your derivative, you're going to be off by 4. So you need a 4. The antiderivative of 2x squared would be x cubed, but you'd be off by 3, so you'd have to divide by 3, so it'd be 2/3 x cubed. The antiderivative of 2x would be x squared, and the antiderivative of 4 would be 4x. And we need our constant here. And as it turns out, we don't need 4 different constants for each antiderivative because you can add the constant that comes from this, plus the constant that comes from this, plus the one from this, plus the one from this. Combine it all into one big constant, c. And so this becomes the antiderivative of this function. So this is the process of antidifferentiation. There's a little bit of guess and check. Just like derivatives, though, we don't have to do this. We have a shorthand notation for it, and we have some rules for antidifferentiation. Looks like there's some formatting errors. So the antidifferentiation process is also called integration, and it's denoted by the integral symbol, which looks like this. It's like a really elongated S that doesn't curve too much. And this is called the integral sign or integral symbol. So if we have, again, this should be integral. If we have the integral of f of x dx, this is called the indefinite integral of f of x, and it denotes the family of antiderivatives of f of x. And what that means is that capital F prime of x equals f of x for all x. And so writing that out a little bit bigger here, we have the integral of f of x dx equals capital F of x plus c. So this here is the integral symbol. The function f of x is called the integrand. This dx is the differential that we studied in chapter 3. And this is then the antiderivative of little f. So this symbol here, the integral symbol, the integral is not the antiderivative. So the integral, just like our differential operator, just tells us to find the antiderivative. So we know that d dx on f of x, this tells us to find the derivative. Actually calculate it out. And the integral of f of x dx, notice that both have differentials because both are related to the derivative. But the integral symbol itself is not the antiderivative. The antiderivative is this function over here, capital F of x plus c. The integral, just like the d dx, just says find the antiderivative. So you can evaluate an integral to get your antiderivative, but we never call this the antiderivative, this symbol. This is kind of the symbol, just like multiplication, division. It's not the actual answer, it's the operation that it's telling us to find. So because of this terminology, integrals and integration, f of x is the integrand, as we said, and that c, its special name, is the constant of integration. And that's because you are integrating and you don't know, it's indefinite, so you're not sure what antiderivative you want. And so it's the constant of integration is what accounts for that. That's what its name is. The differential dx in the indefinite integral, it tells you what variable you're integrating with respect to. So just like here, the d dx tells us differentiate with respect to x. This says integrate with respect to x. So if there's other variables inside your function, if they're not x's and you have a dx here, you are treating them like constants. And the full, again, little PDF didn't like the integral symbol, I guess. The integral of f of x dx denotes the entire antiderivative of f with respect to x. So together, it refers to the antiderivative, but the symbol alone is not the antiderivative. Just like d dx is not the derivative, but dy dx is the derivative of f, or the derivative of y in this case. So when it's all together, the whole thing, integral of f of x dx, that is the antiderivative of f. That's the representation, just like dy dx is the representation for derivative. Okay, so this next box here, the notation, just to review the integral of f of x dx equals capital F of x plus c, where c is an arbitrary constant, and it means that capital F is the antiderivative of f. So it goes both ways. So up here, if you're wondering, well, this seems like exactly what we just did. It is and it isn't. So here we're saying that capital F is the antiderivative, therefore the integral of f of x dx equals capital F plus c. And down here we're saying the integral of f of x dx equals capital F plus c, and that means that capital F is an antiderivative. So it's a two-way street. So up here we're being told in words that we have an antiderivative, so we can construct this equality. If you're given the equality first, you are allowed to safely assume that capital F is the antiderivative. All right, so that's a lot of theory. Let's take a look at the nuts and bolts of integration. So we, just like differentiation, as I mentioned, we do have some formulas to make integrating easier to memorize, essentially, just like our differentiation rules. And the nice thing is, if you know your derivative rules, if you just do the exact opposite of the derivative rules, you will get your integration rules. So let's look at these rules here. So constant rule, we have two of them. So if we integrate a constant times f of x dx, well, we know that derivatives of constants continue through, so it works the same way. Antiderivatives of constants remain the same, so this would be little c capital F of x plus capital C. Now again, notice the little c doesn't need to get multiplied here because even if you did little c times big C, you could just combine into a new constant. So we just write 1 plus c, and that little c sticks along. And the other constant rule is about integrating constants, which we've done a couple times. So the antiderivative a dx, it's the function whose derivative is a, and that's going to be a times x. And then we always need our constant of integration, ax. The next rule is the power rule of integration. So notice we do have a requirement here, n is not -1. Then the integral of x to the n dx. So if we think about what our power rule for the derivative was, it was bring n down and multiply by n and raise it to n minus 1. So the opposite of n minus 1 is n plus 1, and the opposite of multiplying is dividing, n plus 1. And then plus c. So your power rule for integration says raise your power by 1 instead of reducing it by 1, because that's what derivative does. And then divide by the new power instead of multiplying by the old power. So these are truly opposite in every sense of the word. Right, but that's our power rule for integration. Now we have our natural logarithm rule. This is what handles this case that we have to exclude in the power rule. So the integral of x to the -1 dx, which equals the integral of 1 over x dx. This is ln, absolute value of x, plus c. And so there's two ways to think about this. There's one is the direct way. The derivative of ln is 1 over x, so the antiderivative of 1 over x has to be ln. And if we look at it this way, let's say we forget that we can't use the power rule, and we try and add 1 and divide. Well, if we add 1, we get x to the 0. If we add 1 to -1 here, and x to the 0 is 1. So now we've taken something that changes with x and made it a constant. And that's just not going to be okay. So two ways to think about that. If you have an x, you should have an x. So if you forget that this can't be done with the power rule and you lose your x's, you know you need to go back. Or you can remember that the derivative of ln is 1 over x, so the integral of 1 over x is ln, because they need to go opposite. And then our exponential rule for base e to the x dx. Well, the derivative of e to the x is e to the x, so the antiderivative of e to the x is also e to the x, and then plus c. So we have some properties of integrals to help us out as well, just like we did with derivatives. So the first property is called linearity, and it actually encompasses this rule here. So linearity says that you can factor things. So if we have c f of x dx, the reason that it equals this is because of its property of linearity. You can factor the c out, and then the integral of f of x dx. So we've seen linearity before. We saw it with derivatives. You can pull the constant out, they stick around. We saw it with limits. You can pull the constant out, they stick around. And the same applies for integrals. And then sums and differences. If we have the integral of f of x plus or minus g of x dx, well, then we can evaluate these individually as f of x, the integral of f of x dx, plus or minus the integral of g of x dx. So one thing that's important here is, obviously for this rule, plus goes to plus, minus goes to minus. But it's very important that you include your differentials. A lot of students get lazy and they drop this dx here and here, and that's bad for two reasons. One, the differential tells you what your variable is and what your constants are, so you need it to know what you're integrating. And two, if you drop this dx, then your integral is not finished. So if there's no dx here, then the integrand inside of this integral continues until it sees a dx. So this is especially important if you're plugging this into a calculator or a online calculator if you're checking your work. If you don't put that dx, it's going to keep thinking that you're still inputting an integrand, a function here, until you write dx. So it's really important that we remember our dx's. Don't just leave them off. Okay, so let's look at a couple examples here. So this is just applying our rules in combination. So we want to integrate x to the 9th dx. So we're coming up to our power rule. So n is 9. So this is going to be x to the 10th divided by 10 plus c. 9 plus 1 is 10. So that's our final answer. For this integral, we're going to pull out the 5 using linearity. E to the 4x dx. And then e to the 4x should be e to the 4x, 5e to the 4x, plus c. And then you can always check how much you're off by taking the derivative again. So if we take the derivative, this is going to give us 20 e to the 4x. That's too many. It's too many by a factor of 4, so we divide by 4. And so our final answer, so if we divide by 4 here, we divide by 4 here. And our final answer is 5/4 e to the 4x. Now I do divide by 4, but c divided by 4 is just another constant, so we can just write this as plus c. So doing this process of checking your derivative, once you've made your choice of your antiderivative, is really important to get your constants correct. And the more that you do this, the more you'll be able to recognize, oh, this is an e to the 4x. I'm going to have to divide by 4, so I know I'll put it here. And for more complicated versions of this we have in a later chapter, in this chapter, not in a later chapter, what's called substitution. So this is our antiderivative here. For this integral, we're just going to split this into its two pieces, the integral of 5x dx plus 4 times the integral of x cubed dx. I guess I could have brought the 5 out, but this is going to be 5x squared over 2. So we're combining linearity, or our constant rule here, with our power rule. Power rule on the x squared, or on the x, to get x squared over 2. And then the constant rule to say keep that constant that you saw the same. And then plus x cubed should be x to the 4th over 4. So this would be 4x to the 4th over 4 plus c. And this, of course, reduces to 5/2 x squared plus x to the 4th plus c. And our last one here, we want to change this to 7 times the integral of e to the 6x minus the integral of x to the 1/2 dx. And I forgot the dx in here. dx. Sneak that in. So e to the 6x should be e to the 6x. And then if we check our work like we did here on the second one, we'll know that we're going to be off. And you're always going to be off for the e to the x by this number. So I know that this is going to need to be 7 over 6 e to the 6x because it's 6x here instead of just x. And then x to the 1/2. Remember, power rule is for any power other than -1. So even fractional powers count the same. So x to the 1/2's antiderivative is going to be minus x 1/2 plus 1 is 3/2. And then divided by 3/2 plus c. And we never leave our fractions this way. So this is going to be 7/6 e to the 6x minus 2 over 3 x to the 3/2 plus c. And that's our final answer there. So our last problems, or not our last problems, but coming to a close in this section, just 2 pages left. Some practice problems, so just using our integration rules. And again, I'm not sure why it didn't like this one symbol here. That should be integral. So try these out on your own. Follow your rules. Follow your constant rules. Follow your rules for power rule, logarithms, exponentials, all that good stuff. And I'm going to go over them now, so hopefully you have your answers. So this is just a straight application of our rule. The integral of 1 over x is ln of the absolute value of x plus c. This one I'm going to take term by term. So the integral of 1 is x minus 3 over x. So the minus 3 is going to stick around. And then it's just the integral of 1 over x, which again is ln of the absolute value of x. And then this is x to the negative 4. So we're still using power rule. So this is going to be plus x to the negative 4 plus 1 is x to the negative 3 divided by negative 3 plus c. And then finally, the integral of e to the x dx, again, is just a straight application of our rule. This is e to the x plus c. So now we want to talk about initial value problems and initial conditions. So in this next example, we're going to find the graph of the antiderivative y equals 2x for some various values of constant c. And I'm going to pick them. They're not listed here. And then we're going to find the specific antiderivative with f of x where f of 1 equals negative 2. So if we integrate 2x dx, this is 2 times the integral of x dx. Our power rule says this is 2 times x squared over 2 plus c, or 2 times 1 over 2 just makes it x squared plus c. And we are going to let c equal 0, 1, and negative 1. So we're just going to sketch some graphs here, and we're not going to get as specific as our graphing in chapter 3. So we know that x squared plus 0 is just x squared, so that would just be the standard x squared. X squared minus 1 would look basically the same, but starting down here instead. This would be x squared minus 1. And x squared plus 1 would look basically the same, but starting here. So this would be x squared plus 1. So all of these, as we've talked about, are antiderivatives of 2x. But what we want is the specific antiderivative where f of 1 equals negative 2. And so this f of 1 equals negative 2, this is what's called an initial condition. And a question that has an integral f of x dx with an initial condition is called an initial value problem. Initial value problem. To box that up, that's important. Now, I refer to these as IVPs because I'm a mathematician and I'm lazy. So I like to make acronyms for everything. So whenever you're given an integral to solve and you're given an initial condition with it like we are, we're solving an initial value problem. So the way that we do that is we take our f of x and we're going to say this is x squared plus c, and now we're going to plug in our initial condition. So f of 1, which equals negative 2, would be 1 squared plus c. Well, that means that negative 2 equals 1 plus c, so c equals negative 3. which means our final answer, I'll write it here, capital F of x, is x squared, and our new constant is -3. This is the specific antiderivative that we were after. And as it turns out, this is the only way to find what your constant of c has to be. If you're not given an initial condition, you can't find the specific antiderivative that you're looking for. So everything comes down to this initial value problem, unless you just want the general antiderivative. So this here, as I just said, is the general antiderivative. This is a specific antiderivative, which is the result of an initial value problem, where you have an integral and an initial condition. So I've given you a little practice one to try here, an initial value problem of your own. So find the function f such that f prime of x equals x squared and f of -1 equals 2. So try this out. Try and figure out what the specific f I'm looking for is. Pause the video and go. And I will now go over it. So we have the integral of x squared dx, according to our power rule, is x cubed over 3 plus c. And so we're claiming that f of x is x cubed over 3 plus c. F of -1, which equals 2, would equal -1 cubed over 3 plus c. And so 2 equals -1/3 plus c. So adding 1/3 over, we have c equals 6/3 plus 1/3, or 7/3. So our final answer then is f of x equals x cubed over 3 plus 7/3. That is our specific function f that gives us the correct initial value problem solution. So let's take a look to finish up this section. I know we're getting a little long here. Is a couple application problems, word problems. So a rock thrown upward at an initial velocity of 50 feet per second from an initial height of 10 feet has a velocity modeled by v of t equals -32t plus 50. T is the number of seconds after the rock is released, and v is in feet per second. So in part A, we're going to determine a distance function h as a function of t. In this case, distance is the height of the rock, which is why I'm using h. And so to start this problem, we have to remember that our distance, our general distance, s prime of t, equals the velocity function. So that means if we want s, we need to integrate the velocity function. So we're going to integrate. Our velocity function is -32 t plus 50. So this goes in parentheses dt. So remember, our differential is telling us what our variable is. So even if there were x's, which there aren't, you would treat the x's as a constant since we are integrating with respect to t. So using our power rule, we have -32t squared, t goes to t squared, divided by 2, plus 50t plus c. And I'm just going to reduce this a little bit. So we're saying h of t instead of s, because we're talking about height, equals -16t squared plus 50t plus c. And since they gave us an initial condition, you can almost always say initial height or starting height of 10 feet, we know that h of 0 equals 10, which would be -16 times 0 squared plus 50 times 0 plus c. So c equals 10. So our final answer for this section is h of t equals -16t squared plus 50t plus 10. So now we figured out the full model of the height. We got our specific antiderivative, our specific height function. And then it says find the height and the velocity of the rock after 3 seconds. So this is h of 3 and v of 3. So the reason that we're doing this in part B is to distinguish when we should be integrating and when we're not integrating. Because it's really easy to get tripped up at this point in the class of thinking, okay, I've been doing derivatives for so long, now I'm switching to integration. I calculate integrals, calculate integrals, calculate integrals. But we need to be aware that sometimes once you calculate the integral, we just want to know some information. So part B is one of those times. We need to know that, okay, we're not integrating anything, we're just plugging in 3 seconds to our height and to our velocity. And when you plug these in, it's just plugging in into the function. So h of 3 would be negative 16 times 3 squared plus 50 times 3 plus 10. And this ends up equaling 16 feet. And v of 3 is just plugging 3 into the velocity function, negative 32 times 3 plus 50. And this equals negative 46. And remember, v is in feet per second. So this is feet per second. And a classic part C to this kind of problem would be interpret the results, or maybe I could have written interpret here as well. And so you can say, okay, at 3 seconds, the rock is 16 feet in the air, and it's falling at a rate of 46 feet per second. Because remember, when the velocity is negative, it means it's going either backwards from where you started, or in this case, since we're going up, it should be falling down. So this means we're falling down at a rate of 46 feet per second. Okay, so let's move on to the next example here. The rate of change of the population of Arizona is modeled by the exponential function p prime of t equals 0.0416 e to the 0.0315 t, where t is the number of years since 1960, and p prime of t is in millions of people per year. And in 2010, we know that Arizona had a population of 6.4 million. So before we get going, we're going to key in right here and just translate this to math. So this means that our p of whatever number of years that is equals 6.4. And t is the number of years since 1960. 2010 is 50 years later. So this is telling us our initial condition. P of 50 is 6.4. So in part A, when it says find the population, we are solving the initial value problem. Not only do we need to integrate our p prime of t dt, we're going to have to then use our initial condition to find our full value. So this is the integral of 0.0416 e to the 0.0135 t dt. Now this one looks gross because it's decimals, but it's still just an exponential. And if you go back to the previous examples, every time we have an exponential that isn't just an x or a t, or whatever our variable is, we end up dividing by this number. So this is going to be 0.0416 e to the 0.0135 t divided by 0.0135. It always works out that way. And then we can't forget our constant of integration plus c. So then we would plug in our 6.4. And so I'm going to just extend the work area here because I need some more space. So when you divide this, this is 1.3206 e to the 0.0315 t. And this is plus c. This is what our p of t is. So when we plug in 50, 1.3206 e to the 0.0315 times 50 plus c, this should equal 6.4. Well, then we're going to solve for c. So this is a nice big number that you just plug into your calculator and you approximate it. We have 4 decimals, so we're going to approximate to 4 decimals. So when we plug this in, I get 6.3796 at 4 decimals, and this would be plus c equals 6.4. And then we're just solving for c, and c is 0.0204. So our final model, p of t, is 1.3206 e to the 0.0135 t and then plus, I should have written smaller, 0.0204. And so that is the model for part A. In part B, estimate the population of Arizona in 2018. Well, that's P of 58. And the reason we say estimate is because obviously our model is not quite as accurate since we are using 2010 data. We could be using 2017 to get a better idea of what that constant should be. But that's okay for our purposes. So this is just plugging into our function. So this would be 1.3206 e to the 0.0315 times 58 plus 0.0204. And again, this is just putting it into your calculator. I don't expect you to multiply these things or know what e to specific powers are. This comes out to be approximately 8.2282. Again, we're going 4 decimals because we have 4 decimals in our problem. And this is million people. Million people. And as it turns out, the actual population in 2018, was 7.158 million. So we are overestimating here, and if you're wondering why, again, it comes back to what our initial condition was. In 2010, the population was rising, the rate of change, the derivative, was a lot higher in value than it was in 2017. So in 2017, there was a bit of a dip. Actually, I think the dip came in like 2015. But that's what accounts for the change. And so you're always looking at your initial condition. The further away your initial condition is, just like our tangent lines, when we were doing tangent lines in the last chapter, the less accurate they are in those predictions. So if you're taking your initial condition, we could make this even more inaccurate if we looked at, the initial population in this was after 1960. So if we looked at like 1980, we'd be really, really far off. Really far off is relative since we're dealing with millions. So that's the end of 4.1.